All right. This unit, what we're going to be looking at is going to be looking at bonding. So we're kind of, jumping around a little bit, but what we're going to be looking at is bonding. Just how do these atoms, how do they come together to share or do something with their electrons to form compounds? But that's kind of the nature of this unit. So first things first is, why do atoms bond to begin with? So atoms bond because it has to do with their valence electrons. Now we should note here that some of this stuff is a review from what we went over in 9th grade. So like a Bohr model, a Bohr diagram, that's a big thing we do in 9th grade. If you don't quite remember what a Bohr model is, that's okay. You're not going to have to draw those at all. Valence electrons, if you don't quite remember what those are, just a quick recap. Valence electrons, these are the electrons on the outside of the atom. These are the electrons that are basically involved in bonding. And what they're trying to do is, whatever this outer ring is, they're trying to make it full. So that is the motivation for why atoms bond, is that they're trying to get this outer ring completely full of electrons. And again, this is being recorded, I believe, and I will upload this. You have a copy of these notes also on Schoology. So if I go too fast, or if you need to go back and write something down, you can always do that. Okay? So for most atoms, this means that they need to have 8 electrons. It's one of the things from doing Bohr models, was that those rings can hold up to 8 electrons. And this is called the octet rule. This is just the general rule that describes what atoms are doing in trying to become stable. Now there are exceptions, and I would say I would write down this exception right here, that hydrogen only needs 2 electrons. And again, this is a exception in the Bohr model, that the first ring of electrons can only hold 2. Or you can think about it in terms of the noble gases, in that helium, a noble gas, only has 2 electrons. And so that's kind of the reason why hydrogen is one of the exceptions to the octet rule. It doesn't need 8, because hydrogen being so small, 2 will be enough. And again, because it's similar to a noble gas. Just so you know, people at home, the way that my computer is set up going through this presentation, if you're saying something in the chat, I can't really hear it or see it, but I think I have audio alerts set up. Let me just double check in case anyone needs to say anything. Okay. I think I have it set up for an audio alert, so if you have questions at home, you can type it in and we can stop very easily. Okay. So, how do they do this? So here we can look at an example of sodium, where it has 1 valence electron. It has 1 electron in the outer orbital, or we can count all of these on chlorine, and it has 7 in the outer orbital. So one of the things that could happen, so how do they get this full amount, is they could lose. So if this electron all of a sudden disappeared, well then this ring, this second ring, would become the outside ring, and it's totally full. So this is one way that they could get full, is by getting rid of, or they could gain electrons to get up to 8. So here, if we count chlorine, it has 7, so it could just grab an electron and place it right there, and that would give it its 8. So these are the only things that atoms can do, lose and gain, to fill their outer orbital. And in this case, that's exactly what happens. So sodium will lose its electron to become full. Chlorine gains that electron, it becomes full. But, and these are some terms you want to write down, sodium is now positively charged because it has more protons than electrons. Chlorine now has more electrons than protons, and so it becomes negative. So positive ions are called cations, negative ions are called anions. So sodium is a cation, chlorine is an anion, and look, you have something positive right next to something negative. And the universe has always told us from day one that opposites attract. If you've ever seen any kind of romantic comedy, that's what always happens. It's opposites attract, right? Grease, right? Danny and Sandra, whatever her name is. Sandy. And that's what an ionic bond is. Okay? It's those opposite charges attracting to each other. So what you get here is this transfer of electrons, and then as a result, positive and negative charges come up and they stick together. So here's what you really need to know about ionic bonding. Ionic bonding is between a metal and a non-metal. And the reason is because metals typically don't have a lot of valence electrons. So it's a lot easier for them to lose than it is to gain. And non-metals are just the opposite. They typically have a lot of valence electrons, and so it's much easier for them to just gain up to 8 than it is to lose all the way down to nothing. So because of this, because metals tend to lose their electrons and non-metals tend to gain electrons, this is typically what happens with ionic bonding, is we get this transfer, the metals become positive, non-metals become negative, and then as a result, they stick together to form an ionic bond. Okay. So again, I've been trying to, what's highlighted are probably the things that you minimally want in your notes. The other things that are up here are just kind of to give a more well-rounded picture of what's going on, but what's highlighted is kind of the minimum amount of stuff that you want to write in your notes. So that's type number 1. Type number 2 is covalent bonding. Covalent bonding is between two non-metals. And so here, non-metals have a lot of valence electrons. Non-metals do not like to lose electrons. And so here, in this situation, you don't get the same type of thing. You don't have elements that freely want to transfer electrons, because both of these things want. And so as a result, you don't get a transfer. Instead, what they do is they share electrons. That's the identifying factor of covalent bonding, is that they share their valence electrons. And that's how they achieve a full outer orbital. Now, when you share, there are two ways that you can share. You can either share them evenly, or you can share them unevenly. When they are shared evenly, we call that a non-polar covalent bond. The valence electrons are just evenly distributed between the two atoms. Right? It's the picture of two children playing nicely with their toys. Right? It's idyllic, it's nice. Or you can share them unevenly. This is probably, if you have siblings, what you are most used to. That the valence electrons being shared is one is hogging more of them than you. This is you sitting at the breakfast table complaining that they got more milk in their cereal than you did. Or you're playing with your trucks, but they're hogging all of the trucks and won't let you play with them at all, or whatever the case may be. If it was an analogy for the relationship with my brother and I, it would be more involved of blood sport and cage fighting than it is sharing. I don't think we ever shared anything other than insults to each other. But when they're shared unevenly, we call that a polar covalent bond. So those are two terms, nonpolar, polar, that you're going to want to know for the test. So we have ionic, which is metal and nonmetal. We have covalent, which is two nonmetals. And then our last type is the other possibility. What if it's two metals? This is what we call metallic bonding. You don't need to know much about metallic bonding, with the exception of this. So metals don't have a lot of valence electrons, and so they like to give them away to become stable. Well, when you have, like here, all of these zinc or sodium, what you get is this overabundance of electrons. That no one really wants any of these electrons. And so that's where this phrase, sea of electrons, comes into play. Because they're all just there. And all the atoms are kind of just floating around. And the electrons are free to move throughout. This is the reason why metals bend very easily. Because think of, a bunch of inflatable toys in a pool. You can easily pass right through them or move them around because no one's really attached to anybody. Think of all of these extra electrons are there that are free to move around. This helps explain why metals conduct electricity so well. Electricity is just the movement of electrons. Well, these atoms could care less about electrons. And so because of that free movement, metals conduct electricity really, really, really well. So that's kind of serving as my introduction. So here we have these different types of bondings, but the way that these things bond has an effect on how they behave. When you have atoms just floating around in this abundance of electrons, it's going to result in properties that we can see and that we can measure. When atoms share unevenly, that's going to result in chemical properties that we can see and observe. And so this is getting to the last part, is just how does the type of bonding affect the chemical properties? And so there's going to be a couple tables. We're going to look at three, so boiling point, solubility, and conductivity of electricity. Now, what you're going to see are generalizations, and of course there will always be exceptions, but this is just overall, generally speaking, this is kind of how it works. So first, looking at melting and boiling points, and I would just say you really should just write these two columns down. You don't really need to know the why or why not, but just that ionic, for melting and boiling, it's high temperatures. Polar, high boiling and melting. Metallic, low. Non-polar, the lowest. The why or why not just kind of helps us to explain, well, why is that the case? Why do we observe that? Well, if we think about ionic, or think about boiling and melting, is we're tearing these molecules apart. when things become liquids or gases, the molecules are spreading out. We're trying to pull these things apart. Well, an ionic bond is incredibly, incredibly strong. And so it takes a high amount of energy to pull those things apart. And then if you're making a table, your next column can be the next property we're going to look at, which is solubility. So ionic and polar covalent compounds tend to be soluble in water, meaning when you put them in water, they will dissolve. And then likewise, nonpolar and metallic compounds tend to be insoluble in water. Meaning, if you were to throw a paperclip into water, it won't dissolve. Or if you were to pour oil into water, it won't dissolve into the water because oil is nonpolar. Whereas if you take salt, it readily dissolves in water. If you take what's something polar? Sugar. Sugar is a polar molecule. It readily dissolves in water. And then your third column will be for conductivity. So this is, does it conduct electricity? So metals, yes, obviously. For ionic, yes, but make sure you write this down, is that ionics only conduct electricity when they dissolve in water, and then covalent compounds do not conduct electricity at all. I'll put that back.